Chapter 22 Chemistry, Theory Video 7. Catalysis is what we are going to discuss about. So, you know that a catalyst increases the rate of a chemical reaction. So, how they do it is by providing an alternative pathway for the reaction to occur with a lower activation energy. So in chemistry, there are biological catalysts as well. In chemistry, we mostly talk about non-biological catalysts. Many transition elements are catalysts in the chemical reactions that take place. Then there are two kinds of catalysts, two classes of catalysts that we can discuss about: homogeneous catalysts and heterogeneous catalysts. For example, if you take a homogeneous catalyst, homogeneous catalysis will occur when the catalyst is in the same phase as the reaction mixture. Now, when esters are to be hydrolyzed, hydrogen ions will catalyze the reaction mechanism. So CH3COO C2H5 aqueous, when you add water to that, the H plus ions will make it into CH3COOH and C2H5OH. So all the reactants products are the products as well as the catalyst are all in the same aqueous phase. Now, when you take heterogeneous catalysis, when the catalyst is in a different phase to the reaction mixture. When you talk about the decomposition of aqueous hydrogen peroxide using manganese 4 oxide. So 2H2O aqueous, MnO2 solid, 2H2O and O2. So manganese 4 oxide is in solid phase, hydrogen peroxide is in aqueous solution form. So as a result, that is heterogeneous catalysis. Now, homogeneous catalysis is what we are going to talk about. In homogeneous catalysis, most of the time it involves changes in oxidation number of the ions involved in catalysis. For example, if you consider iodide ions which catalyze the decomposition of hydrogen peroxide, what happens is iodide ions would be first oxidized to iodate ions, IO minus. Then IO minus, the iodate ions will go into further reaction. Molecules of, it would react with more molecules of hydrogen peroxide and would be converted back into iodide ions. So now the principle the main principle of catalysis is the catalyst does not get used up. It has to remain in the same form at the end of the reaction. So that principle is obeyed here. Now, as you can see in the first equation, H2O2 plus aqueous plus iodine gives H2O plus iodate, IO minus aqueous ions. Then H2O2 will react further with IO minus aqueous to produce H2O I minus plus oxygen. So that I minus can again react with another H2O2. So the overall reaction would be 2H2O2 aqueous, 2H2O liquid plus oxygen and iodine in the presence of iodine. So the transition elements are good catalysts because they have the ability of changing their oxidation numbers. So before we go into that part, let's write down a note for what we have learned so far. Write down the topic catalysis. A catalyst increases the rate of a chemical reaction by providing an alternative pathway for the reaction to occur by lowering the activation energy. Leave a line, put a star and write down. Many transition element compounds are good catalysts because they have the ability of changing their oxidation number. Leave a line and write. There are two main classes of catalysts. Number one, homogeneous catalysis. When the catalyst is in the same phase as the reaction mixture. For example, hydrolysis of esters using hydrogen ions. Write this equation: CH3 COOC2H5 aqueous plus H2O liquid in the presence of H plus aqueous, giving you CH3 COOH aqueous plus C2H5 OH aqueous. Reactants, products and catalysts are all in aqueous phase. Do line and write. Number two, heterogeneous catalysis. When the catalyst is in a different phase to the reaction mixture. Example, decomposition of aqueous hydrogen peroxide using solid manganese 4 oxide. Write down this equation: 2H2O2 aqueous MnO2 solid plus 2H2O liquid, giving oxygen gas. Then write down homogeneous catalysis. Most often, homogeneous catalysis involve change in the oxidation number of the catalyst. Example, catalysis of H2O2 to water and oxygen in the presence of iodine. Iodide ions are first oxidized to iodate, IO minus ions. I minus is first oxidized to IO minus ions, which react further with hydrogen peroxide to break down hydrogen peroxide and to be converted back again into iodide ions. And write these two equations. Overall reaction is 2H2O2 aqueous plus 2H2O2 aqueous giving 2H2O liquid plus oxygen gas, and it is iodine in the final product. Iodine is the catalyst that should be in this thing, and it is not involved in the final product formation. That is, it is not there as a constituent part of the chemical reaction because it remains the same. Homogeneous catalysis. Most examples of homogeneous catalysis involve redox reactions. So that means reduction and oxidation both take place at the same time. Now, iodine peroxodisulfate reaction. Peroxodisulfate or persulfate ions S2O8 2 minus oxidizes iodide ions to iodine. It's a very slow reaction. S2O8 2 minus aqueous plus 2I becoming 2 sulfate ions and I2 aqueous. Both peroxodisulfate and iodide ions both have negative charge. So in order to collide and react, they have to have considerable energy to repel the to overcome the repulsive forces, because they are both negative. They have repulsive forces, so they repel one another when they come for collisions. But so as a result, there should be more energy that should be supplied to make the collisions occur. So what we can do is we can introduce Fe3 plus aqueous ions to catalyze the reaction. So now we know that it is all aqueous, therefore this is homogeneous catalysis. So this catalytic conversion involved two redox reactions. Now the first reaction is going to be reduction of Fe3 plus ions to Fe2 plus ions by I minus ions. Now the main equation is, please disregard this practical activity for the moment, is S2O8 2 minus aqueous plus 2I turning into 2SO4 2 minus aqueous plus I2. So now in the first step, what happens is 2Fe3 plus aqueous will join hands with 2I aqueous to produce 2Fe2 plus aqueous plus I2. Then what happens is the oxidation of Fe2 plus ions back to Fe3 plus by S2O8 2 minus ions. So the Fe2 plus ions will join hands with S2O8 2 minus aqueous to produce 2Fe3 plus aqueous plus 2SO4 2 minus aqueous. So this is done by the positive negative interaction. Because unlike charges attract, they are very likely to occur when they collide, because the repulsive force, we don't need any energy to overcome any repulsive forces. The reaction occurs with Fe3 involvement. So ultimately the same products will be produced. The reaction is more likely to occur than the direct reaction between S2O8 2 minus and I minus ions. Now it doesn't really matter what the order of the reaction is going to be. First, the Fe2 plus ions might be the oxidation of Fe2 plus ions to Fe3 plus might happen first, and that might be followed by Fe3 plus reaction. So it can be catalyzed by Fe3 plus as well as Fe2 plus. So that is, if you have a sample of Fe3 plus or Fe2 plus, you can use any of them to catalyze this reaction. So this 22.16 gives an energy level profile for the catalyzed and the uncatalyzed reactions. Now because there are two stages in this reaction, as we saw there are two reactions, because of that there are two humps in it. In the uncatalyzed reaction, because it is a single reaction, it involves only a single hump. I hope it makes sense as well. So then there is another thing that you need to understand. For catalysis to work, the standard electrode potential, I hope you can remember this. The standard electrode potential for the reactions involving the catalyst must lie between the electrode potentials involving the two reactants. So that is also something that you must understand here. So here, if the catalysis is possible, is something, this is actually something that we have learned earlier. Now S2O2 2 minus lies here. It has a value of 2.01. Then I2 turning into 2I stands here. Then Fe3 plus 2, Fe2 plus stands here. So it is possible because it lies in between. Right. Write down a note on this. Examples of homogeneous catalysis. The iodine peroxide disulfate reaction. Write down the equation S2OA2 minus aqueous plus 2I minus aqueous giving 2SO4 2 minus aqueous plus I2 aqueous. The direct equation is very slow because both the charges are negative and they need a higher energy to overcome the repulsion when colliding. This reaction can be easily carried out by the presence of Fe3 plus or Fe2 plus ions, which would act as catalyst, which would act as the catalyst. Write these two reactions. Because, after writing the two reactions, write down, because the collisions occur between the positive and negative charges, the required energy for collision is lesser. As a result, reaction is more likely to take place. This reaction can be catalyzed by both Fe2 plus and Fe3 plus ions. I hope you understood. The enthalpy profile for the catalyzed and uncatalyzed reactions is shown below, and then draw this energy level profile. As you can see, there are two steps in the catalyzed reaction, therefore there are two humps. I hope that you are not confused about that. Then write underneath that, in order for catalysis to work, the standard electrode potential for the reactions involving the catalyst must lie between the electrode potentials involving the two reactants. In this, Fe3 plus Fe2 plus conversion lies in between, therefore catalysis is possible. Right. Now, when we look at the practical activity 22.1, so this is how we can do this. What we can do is we take 10 cubic centimeters of 0.5 mole per cubic decimeter sodium potassium tartrate into a 250 beaker. Then we add 10 cubic centimeters of 2m hydrogen peroxide and stir. Then we warm the beaker. So these are steps that are involved in it, and we note the signs of reaction. So the bubbles would come out. Then you stop heating and add cobalt chloride. Then you have to describe the particular results that happens. So then you take the heterogeneous catalysis. You take hydrogen peroxide and different portions of other MnO2, Cu2O, MgO, Fe2O3, Al2O3. So these materials would be added separately to find how they would react. Then you have to compare these to find their catalytic power. So that is something that you need to understand, and in paper 5, when we discuss paper 5, you will be able to understand it better. Now, oxides of nitrogen and acid rain. You have learnt about acid rain in detail when oxides of sulfur dissolve in the water, it contributes to acid rain. So sulfur dioxide will be oxidized to produce sulfur trioxide, SO2 gas plus half O2 giving SO3. There is nitrogen 4 oxide present in the atmosphere, it coming from a variety of sources. This can catalyze the oxidation of sulfur dioxide. And the nitrogen 4 oxide is reformed with this reacting with oxygen in the atmosphere. So SO2 reacts with NO2 to produce SO3 and NO. So that is another example for catalysis. NO plus half O2 becoming NO2 back again. Write down oxides of nitrogen and acid rain. Sulfur dioxide produced from the burning of fossil fuel causes acid rain because nitrogen 4 oxide in the atmosphere catalyzes the oxidation of sulfur dioxide to sulfur trioxide. Write down the first equation and then write the catalytic conversion is the SO2 plus NO2 gas giving SO3 gas plus NO. Nitrogen monoxide reacts with oxygen to produce NO2 once again, and write these two separate equations. I hope you understood. If you understand, please do question number 13. Now, after you have done the question, let's move into this heterogeneous catalysis. So here what happens is they are in different phases. Now usually this involves gaseous molecules reacting at the surface of a solid catalyst. Usually the catalyst is a solid, and on the surface of the solid these gases would react. We use the theory of adsorption to explain this mechanism. Chemical adsorption, or this is also known as chemisorption. This would occur when molecules become bonded to the atoms on the surface of a solid. We have discussed about adsorption earlier. So transition elements such as nickel are going to be good adsorption materials or chemisorbing materials, especially for hydrogen gas. So in here what happens is nickel the atoms on nickel surface have the ability of attracting this hydrogen, weakening the bond between hydrogen, and having hydrogen attached to each nickel atom. So the hydrogen is able to take part in a variety of reactions because it develops a charge now, because it has H plus charge now. It is broken apart. Now when you consider the word adsorb, now absorption is not what happens here. It does not take it in. Adsorb is bonded to the surface of a substance. Now in adsorption of hydrogen, hydrogen gas would diffuse to the surface of the nickel. So they are physically attached or adsorbed onto the surface. There would be there would be very weak forces that would link the hydrogen molecule onto nickel. So when hydrogen becomes chemically adsorbed, that results in stronger bonds that to be produced between each individual atoms of hydrogen and nickel. Then the hydrogen-hydrogen covalent bond weakens and they almost separate. Then the catalyst, when the reaction on the catalyst is going to it is complete, the bond between the products and the catalyst will weaken. So then it would go away. That is, after the reaction has occurred, after it has been taken by something, this is going, it would break away. This is going to be known as desorption. Write down a note on this. Heterogeneous catalysis. This usually involves gaseous molecules reacting at the surface of a solid catalyst by the mechanism of adsorption. Example, hydrogen molecules form weak bonds with atoms on solid nickel surface. The bond between nickel and individual hydrogen atoms becomes stronger and the hydrogen-hydrogen HH covalent bond weaken. This allows hydrogen to react with another substance. After the reaction, the bond between the product and the catalyst would become weaker and they break away in a process known as desorption, desorption. Right, so now let's look at some examples of heterogeneous catalysis. So iron in Haber process. Now we have discussed about iron taking part in Haber process. When converting nitrogen and hydrogen to ammonia, different temperatures and pressures are needed. And we know that this reaction is catalyzed by iron. So how it works is by allowing a surface. Iron allows a surface for hydrogen and nitrogen molecules to come close together on the surface of it. So what happens is, by using the adsorption mechanism, hydrogen and nitrogen molecules come close to the surface, and after that adsorption occurs and hydrogen and nitrogen are separate. Now then hydrogen and nitrogen would start forming bonds and new bonds would be formed, and thereby there would be different steps involved in the reaction, and finally desorption would take place and they will diffuse away. I hope you understand what happens here. Write down. In the Haber process, the production of ammonia from nitrogen and hydrogen is catalyzed by iron. Please draw the 22.19 figure, then it would be easier for you to understand it. Write down first step, diffusion, N2 and H2 diffuse to the surface of iron. Number 2, adsorption occurs, which makes the bonds between the HH and NN bonds to weaken, and the HH and NN bonds to be weak, and it would be strong enough to hold them there until the reaction takes place. Number 3, reaction, adsorb nitrogen and hydrogen, react on the surface of the iron to form ammonia. Number 4, desorption, bonds between ammonia and surface of iron weaken and eventually are broken. So this particular part is actually not relevant here. Weak enough to break bonds, that happens at the stage of desorption. I hope you understand that, obviously, because after H is broken, it doesn't go away from there. It is still there, attached to the surface. Then after reaction occurs only, it will be allowed to go. Then finally, diffusion, fifth stage, ammonia diffuses away from the surface of the iron. So adsorption, all bonds breaking, new bonds forming. After that, desorption takes place. So that is the steps. First, the old bonds would break and new bonds would be formed, and desorption would take place. So that, I hope that makes sense. Now, transition elements in catalytic converter. Now you have learnt about catalytic converter. For many vehicles, catalytic converters are fitted to these to reduce the amount of harmful nitrogen oxides escaping into the atmosphere. So when the catalytic converter is warmed up, the catalyst will speed up the conversion of nitrogen oxides to harmless nitrogen gas, and carbon monoxide would be catalyzed to carbon dioxide, which is harmful, but still it is less harmful when compared with carbon monoxide. Then hydrogen, the unburnt hydrocarbons will also reduce nitrogen oxides in the catalytic reaction. So usually what happens is 2NO plus carbon monoxide gives N2 and CO2, and 2NO2 plus 4 carbon monoxide gives N2 and 4 CO2. In the honeycomb structure, we have discussed this. In the honeycomb structure inside the catalytic converter, there would be small beads coated with platinum, palladium and rhodium. Right? So there is honeycomb, means there is lot of surface area provided for these to take place. So they act as heterogeneous catalysts. So what happens is adsorption of nitrogen oxides and carbon monoxide will happen on the catalyst surface. Then the covalent bonds are weakened between nitrogen oxides and carbon monoxide. Then new bonds would be formed by joining adjacent nitrogen atoms and carbon monoxide and oxygen to produce carbon dioxide. So NO bond would be weakened. So NN, if this is let's say platinum, then NO bond would be broken here, and let's say another platinum is here, NO bond would be broken here as well. So then what happens is these two nitrogens will join up to produce N2. Then if there is a carbon here, another oxygen here, they will produce carbon dioxide. So like that, it takes in a step, not in a single step. In few steps, it will be converted into the less harmful materials, and the bonds, the desorption would take place, and they will leave. I hope you understand that. If you have any questions, please ask. Write down. Transition elements in catalytic converter. Catalytic converters fitted to exhaust systems of vehicles reduce the amount of harmful nitrogen oxides escaping to the atmosphere. Also, it converts carbon monoxide to carbon dioxide. So write down these two equations. Catalytic converter is made up of small beads coated with platinum, palladium and rhodium, which acts as heterogeneous catalysts because they are in solid form. In this, adsorption of nitrogen oxide and carbon monoxide occurs on the catalytic surface. Their covalent bonds are weakened, and new bonds would be formed between adjacent nitrogen atoms and carbon monoxide with oxygen. This will produce N2 and CO2. Their bonds with the surface would weaken, and they get and desorption would take place, allowing them to leave the system. I hope you understood. If you have any questions, please ask. If not, please do the end of chapter questions and the in chapter questions.